In this video, we're going to look at the derivatives of the trig functions. There are proofs that show why these derivatives are the way they are. I'm going to put those in a separate video. That link will show up in the description underneath this video, along with the links to practice problems and also to the previous and next video. So let's get started and look at this set of derivatives that you're going to have to memorize. All right, don't know a single calculus teacher that will let you write these down, but I guess there could be, but I haven't met them yet. All right, yeah, but there's a pattern, so you need to look at these. So notice that the derivative of sine is cosine, right? Kind of makes sense. And the derivative of cosine is sine, but this sine has a negative right here. Now, the derivative of tangent is secant squared x. The derivative of cotangent is cosecant squared x. Has a negative right here. The derivative of secant x is secant x tangent x. And the derivative of cosecant x is cosecant x cotangent x. Sometimes you'll hear me leave the x's off and just say cosecant cotan because we know there's an x in there. Notice that all of the trig functions that start with a c, their derivatives are negative. Okay, so everyone that starts with a c, their derivatives are negative. The other ones are positive. Notice there's sort of a pattern. Tangent goes with secant squared, cotangent goes with cosecant squared. Secant goes with secant tan, cosecant goes with cosecant cotan. So if you kind of use those little ideas on how to memorize these, it's not quite as bad as trying to memorize them as 6 individual, totally unrelated, unpatterned derivatives. There is sort of a pattern to this. All right. Now, they define these in terms of x, but keep in mind, because they don't normally say this so much in your books, there's certainly examples to explain it to you, so will your teacher. But if what the argument is, which is where the angle is, where you're taking sine and cosine, if that is itself differentiable, then you have to loop back in and take the derivative of the inside. So it would look like this. If you had a function that was equal to sine of x, and I wanted the derivative of it, you would say, well, the derivative of sine is cosine of x, because it's just an x. As a matter of fact, if you looped back in here and took the derivative of the inside, it would be just a 1, so it wouldn't change anything. Whereas if you had y is equal to cosine of something like 2x, then the derivative of cosine is a negative because you take the derivative of the outside. The derivative of cosine is negative sine. Leave the inside alone and loop back in and take the derivative of the inside. So this too does not multiply inside that angle. It multiplies all the way out here. So this would be negative 2 sine 2x. Be careful not to multiply inside. It's like trying to multiply inside a square root. Okay, let's try a few problems. I want to work these two kind of in comparison. So what if we have y is equal to cosine of 4x squared? Now in this case, the square just applies to the 4x, to what would be theta, right? Now I could say the derivative was y prime. I could say the derivative is y with respect to x. Let's try that. Now, the outside is cosine because technically this is the cosine of this part right here. Okay? Maybe that'll help you kind of see the inside from the outside. So you take the derivative of the outside, which is cosine, so you take the derivative of that, which is minus sine. leave the inside alone. So you'd have 4x squared. Loop back in and take the derivative of this inside. Now, the inside is a power rule, correct? So you bring the 2 down, leave its inside alone, take 1 off the power, correct? And loop back in and take the derivative of that. And I know people go, well, when do you get to stop? All right, but think about it. If you have 4x squared, if that's all that showed up, and I asked you to take the derivative, if this was in parentheses, you would say, all right, bring the 2 down, leave the inside alone, take 1 off the power, loop back in. So all of this right here is not like you looped in a bunch of times. You're just taking the derivative of that one piece. Okay? Now you have to sort of clean this all up. So you have 2 times 4x is 8x times 4 is 32x. You have this negative sine of 4x squared. Okay? Now what if you have y is equal to the cosine squared of 4x? See how this square over here, the one we just did, this square out here is right next to the 4x. This square is that little shorthand kind of method you learned in trig where it actually means the cosine of 4x, this entire thing squared. Okay, see the difference between the two? All right. I strongly suggest that if you have one of these where it's squared or cubed or whatever, that you go ahead and write it in this sort of power traditional sense where it's outside as opposed to hidden in here inside will save you some pain. So rather than y prime, just for something different, let's do dy dx. Now, this outside is the power. This outside is actually, the original outside is the cosine, then this was the outside once you looped back in. So this is a power to start with. You bring the power down, you leave the inside alone. Take 1 off the power, loop back in and take the derivative of cosine of 4x. So what we're looking at right here is this cosine of 4x, as if the rest of it's not there. So cosine is on the outside. You take the derivative of the outside, which is minus sine. You leave the inside alone, which is the 4x. And then you loop back inside this and take the derivative of the inside, which is 4. May need to stop or rewind and see how this goes. Guess you don't actually rewind to these. All right, now, how much of this goes where? All right, the sine of 4x goes together. The cosine of 4x is joined together at its hip. You have 4, you have this minus, and you have this 2 way on out here. So you have minus 8 cosine of 4x, sine of 4x. And if you look at this and you think, you know what, that cosine 4x, sine 4x, I'm kind of wondering if that might be something like the double angle formula for the sine of 2 theta equals 2 sine theta cosine theta if theta was actually a 4x. Okay, so if theta was a 4x, This would be cosine of 4x. This would be sine of 4x. And this would be sine of 2 times 4x, correct? So let's see what that would do. Minus 4 times 2. And most people are used to learning it sine theta cosine theta, so let's go to sine 4x cosine 4x just to kind of make us feel more comfortable. Sometimes that just helps you save a few points here and there if you're make yourself comfortable. So you have minus 4 sine, and what you have is sine of 2 times 4x, so it's sine of 8x. Now, see how these compared in complexity and the number of steps it takes you to get down to your final answer? All right. So let's move on, see what we can do. When you go into this section of your calculus book, a lot of students have trouble remembering their trig identities and looking for ways to simplify things. You might want to go find like a formula sheet and look it over and kind of get used to it. I want to show you something. Let's do y is equal to tangent x cosecant x. And so we're going to practice this because, whoops, because we haven't done tangent and cosecant yet. All right. Now, tangent x and cosecant x, that's the product rule, right? So let's do y prime. Y prime is, it's the first, which is tangent x, times the derivative of the second. And the derivative of cosecant x is negative cosecant x cotangent x plus, then it's the second times the derivative of the first. And the derivative of the first is secant squared x. Okay, so when you clean this up a little bit, right, this tangent x and this cotangent x multiply to 1. So you have minus cosecant x plus cosecant x secant squared x. And you could factor out a cosecant x. That looks tempting, right? So you have cosecant x times minus 1 plus secant squared x equals. So here you have cosecant x again. This, and you may not have thought about this, but secant squared x is actually 1 plus tangent squared x. Now, I have to admit that I don't particularly have those memorized to the point where I can just quickly, I was going to say regurgitate them, but spit them out, for somebody. But what I have is I can do this very quickly. So most students remember that this basic sine squared x plus cosine squared x is equal to 1. And when you see things like this, like secant squared or 1 plus something, you think, oh man, it's probably related to that. And since I'm trying to figure out what secant squared is and how it relates to anything, if it relates, then secant squared is 1 over cosine squared. So this drives what I'm going to do. I want 1 over cosine squared to figure out the secant squared. So I have to divide everybody by that. So this ends up 1 plus tangent squared x equals secant squared x. So if I think I need it, I just go back over here and kind of rework that back out so that I don't have to add that to my memory list. Some of you may have that memorized. All right, so then this minus 1 plus this one go to 0, right? And I have cosecant x times tangent squared x, which turns out to be 1 over sine x times sine squared x over cosine squared x, which is sine x over cosine x, because this cancels one of those, times 1 over cosine x. So this is tangent x secant x. Now, I still have a hard time giving up these parentheses, depending on who your teacher is. They may want those parentheses around these arguments. A lot of the books are giving these up. I think they just think it makes it clearer, but I actually think sometimes it's easy to lose who's doing what. All right. Now, this took us 1, 2, 3, 4, 5, 6, 7, 8 steps, and we had an answer, right? Plus a little bit of work over here. Okay. Now, I want to show you something that you could have done. So if you had y is equal to tangent x cosecant x. Okay, so tangent is sine of x over cosine x times 1 over sine x. So the two sine x's cancel, and you have 1 over cosine x, which is secant x. Okay? Now, you haven't taken any derivatives yet. This is still the original function. So depending on how quickly you could get through this change, some students can look right here and say cosecant is 1 over sine. It's going to cancel into the sine on the tangent, and then they can go straight from there to here. And some students go a little bit slower, and that's fine. Like I said, it's better to go slow and correctly than fast and in the wrong direction. So now we're down to y is equal to secant x, and the derivative of secant is secant x tangent x, which gets us to here. So it is worth your while in all of your calculus, but especially in the trig, to look at a problem and say, can I attack that slightly different? Can I simplify things? Can I rearrange it? Especially if you could tell that the way it is, it's going to be kind of a lot of procedures, a lot of steps. Maybe you can do something to manipulate the original question so that it makes it easier for you to solve it. And you may think, why is that? Why do calculus teachers do this to you? Okay. So it kind of boils down to this. In the past, many of you have not ever tried that, where you look at a problem and say, I wonder if I rearranged that or multiplied this out or cleaned that up, if that would make it easier. You've just accepted what you've been given, and you do the best you can with what's been given. But when you go off into your majors and when you go off to your professions, you're going to go into everything from medicine to research to construction engineering to physics. I don't know where you're going to go. But sometimes what you're asked is to look at things, maybe it's individual things like inputs, and they have all of these inputs and they want you to come up with some way to have all the inputs sort of integrate together, and you're going to come up with a way to solve it or process it. Maybe it's something that already exists and they want you to look at it and see if there's some way that you can improve it. Maybe it's a list of patients' behaviors or what they're feeling or the test results, and you need to combine all that and come up with a diagnosis. So learning to look at something and take just a little bit of time and look it over and see if you can find any information in it that might be helpful. That slight pause is great practice for what could be coming up in your future. All right, so let's try this one. And you might want to stop the video and give it a shot and see how you're doing. If you're going to attempt this, one possibility is to square this so that you can see the squares. At any rate, stop the video and try something. Then turn it back on. Don't go away. Now, assuming you're back, okay, one possibility would be to say, all right, this is the power rule, and you'd say 2, leave the inside alone, take 1 off the power, right? Loop back in and take the derivative of the inside, plus bring the power down, leave the inside alone, take 1 off the power, loop back in and take the derivative of the inside, and since they're just x's, you don't have to loop in. So this turns out to be minus 2 cosine x sine x plus 2, and you could rewrite this if you want, cosine x sine x, which goes to 0. But if you took just a minute, isn't cosine squared x plus sine squared x equal to 1? And the derivative of 1 is 0, and you're done. Okay, so always take a minute. Always take a minute. Let's look at y is equal to 1 plus tangent squared x cubed. I want to stop the video and give it a try. And if you're back, you would go, oh wait, 1 plus tangent squared is secant squared x cubed. And secant squared x cubed is secant x. I should do this the way your book does it. Secant x. Well, most likely your book does it. To the 6th, because these are going to multiply. Now, you haven't taken the derivative yet. You've just rearranged it. So y prime, you bring the power down, leave the inside alone, take 1 off the power, loop back in, and take the derivative of the inside. So it turns out to be 6 secant to the 6th x tangent x. Now you can imagine that if you had done this one straight without replacing it with potentially something more straightforward, y prime would be bring the power down, leave the inside alone, take 1 off the power, loop back in and take the derivative of the inside. The derivative of 1 is 0. The derivative of tangent squared x is 2. Tangent x. The derivative of tangent is secant squared x. And eventually you would get down to there. But it took me about 1, 2, 3, 4, 5, 6 steps. Okay, so give it a try either way and see how you did. Let's try this one. Y is equal to the square root of cosine x sine x. Now, we're going to take a second and we're going to see if there's something interesting that we could do. Like if this had been cosine x times secant x, that would have been 1, right? Or cosine x times cotangent x, right? I don't know. We could try something, but there's nothing you can do with a cosine times a sine. Now, derivatives don't understand or work with square roots. They work with powers. You'll hear me use a lot of terminology like not happy or doesn't understand or whatever, because to me, these are all just little people that I'm working with, with little stories to tell, and it keeps me entertained. All right. So here we go. The outside is a power, so you bring the power down, leave the inside alone. Take 1 off the power, loop back in, and take the derivative of the inside. And the derivative is this product right here. So it's the first times the derivative of the second, and the derivative of sine is cosine, plus the second times the derivative of the first, and the derivative of cosine is negative sine. So it's 1/2 cosine x sine x to the minus 1/2 cosine squared x minus sine squared x. And I was kind of hoping that I might get something like cosine squared x plus sine x squared x, because that would be 1. I like that one. Always makes me smile, but it didn't. So this is cosine squared x minus sine squared x over the 2 is in the denominator. And since they started off asking me this with a square root, I need to convert it back to a square root and put it down into the denominator, because this negative is not happy. So it wants the other side of the fraction bar. Now, your teacher or I might be happy with this answer, but if somebody went the extra mile and said, you know what, this cosine squared minus sine squared is actually cosine of 2x, I'd probably give them extra credit for remembering that much of their trig. And then some of your teachers are going to say, I think you should be able to do that without extra credit. So if you want full credit, you'll have to do that. All right. Now, let's look at what if y is equal to cosine of 3x plus 4 over sine of 3x plus 4. Now, if you leave it in this state, you're going to do the quotient rule, and it would look like y prime is the bottom times the derivative of the top. And the derivative of cosine of 3x, you take the derivative of the outside, leaving the inside alone. Loop back in and take the derivative of the inside. Now that's just the first part. Whoops. Well, I don't know what that was. All right. Minus the top times the derivative of the bottom. So the derivative of sine is cosine. Leave the inside alone. Loop back in and take the derivative of the inside all over the bottom squared. Or, see, and then you would have to do a lot of cleanup, right? Or you can notice that cosine of something over sine of the same thing is cotangent of that. And the derivative of cotangent is negative cosecant squared. Leave the inside alone. Loop back in and take the derivative of the inside, and you'd have minus 3 cosecant squared 3x plus 4. Or you can do all of this work and get over there. And it took me quite a lot of space and 1, 2, 3, 4, 5 lines to get there. Okay? Now let's do one more. And we have y is equal to sine theta plus cos plus cosine theta over sine theta minus cosine theta. And these do not cancel. So the two sine thetas don't cancel and the two cosine thetas don't cancel because they're not factors. All right. Got little hands holding on. Go see the previous video about factoring. All right. So here we go. This is going to be quite a lot of space to take up. All right. So it's the bottom times the derivative of the top. So the derivative of sine theta is cosine theta. And the derivative of cosine theta is minus sine theta. Plus the minus the top times the derivative of the bottom. The derivative of sine theta is cosine theta. The derivative of minus cosine theta is minus a minus, right? Minus a minus sine theta. So it turns out to be plus sine theta. All over sine theta minus cosine theta squared. And when you multiply all that out, you get sine theta cosine theta minus sine squared theta minus cosine squared theta plus cosine theta sine theta minus sine theta cosine theta minus sine squared theta minus cosine squared theta minus cosine theta sine theta. If you find a faster way to do this, I would love to see it. Write it in the comments. Okay, over sine theta minus cosine theta. I had kind of an idea about how to do it faster, but this is good practice. All right. And when you clean up all those things that cancel out, right, then what you get is minus 2 sine squared theta minus 2 cosine squared theta over sine theta minus cosine theta squared. And you think, all right, I'll factor out a minus 2. So that gives me sine squared theta plus cosine squared theta, my favorite identity. I don't know, I've always liked it. My students like it. I don't know if you like it. And sine squared theta plus cosine squared theta is equal to 1. And 1 times negative 2 is negative 2. And this is sine theta minus cosine theta squared. Now, that might look just fine to you, and you might want to box it in there, but I want to just try something for a second. So minus 2. If we multiply out that binomial square on the bottom, you would have sine squared theta minus 2 sine theta cosine theta plus cosine squared theta. And you go, hey, look, this right there is cosine squared theta plus sine squared theta, so it's 1. So minus 2 over, and you've got 1. And this part right here is that double angle. So it's minus sine 2 theta. So maybe pull the negative out. All right, now you may have thought, if you were doing these, that this right here looks just fine. Okay, in your mind that's just fine. in your mind, you're not seeing why going that down there is that much better. I actually think it does look a little bit better, and I actually think it's worthwhile trying to go down that far because you actually managed to implement two identities. This one that gave you 1 and this one that gave you the double angle formula. So I think it's actually well worth that little extra few steps to get 2 more identities put in there. Only you would know whether your teacher would be happy with this answer or whether they're going to be wanting you to take it on down to this answer. And that's something that you just need to get kind of used to with your teacher. But going these extra couple of steps, even if your teacher would have been happy up here, maybe they'd give you some extra credit for going the extra 2 steps. I don't know. All right. But what I do know is it is well worth your time to try to look at the original problem and see if you can manipulate it before you get started to something easier. And it is well worth your time to look at the answer that you're considering boxing in right here and determining if there's something you might be able to do with that to clean it up just a little bit more. And like I said earlier, this is good practice for you for your future because in a lot of the jobs that you have, you're going to be trying to create something that isn't there or a piece of knowledge that you haven't acquired yet. So there may be little bits and pieces that you're going to have to take and make into a new whole or a new idea or a new concept. So please try to think of this as just a way to get your brain used to thinking outside the box. It is not like some sort of torture that your calculus teacher is trying to inflict on you or anything. We are actually trying to get you to learn how to think in new ways and to apply your brain in a new concept of planning and looking ahead and thinking about and reflecting on where you are before you decide you're done. Please don't forget to look in the description section for the link to the proofs. Please don't forget to subscribe and to like the video, and I will see you in the next video.